Okay, so now looking at how does the C affect the rate of reaction? The relative reactivities of the alkyl halides is that the less electronegative the alkyl halide, the more reactive it is. And so Ri is going to be the most effective or have, and remember what we're trying to do. For our alkyl halide, the carbon to halogen bond is the bond that is breaking. And so the weakest bond is going to give us the best reactivity. We want to break this bond. So the weakest bond has the weakest bond gives us the most reactive alkyl halide. Weakest bond to X will be the most reactive. And remember your bonding trends. Bond strength bonds get longer and weaker as we move down a group. So fluoride has the shortest and strongest bond, and iodide has the longest and weakest bond. And so that is why Ri is the most reactive. Having iodide is the most reactive for the alkyl halide. We can look at the rates of reaction for the alkyl halide. The rate of breaking the Ri bond is 30,000. To break the carbon bromide bond is 10,000. To break the carbon chloride bond is 200. And to break the carbon fluoride bond is 1. And so the most reactive alkyl halide has the most acidic conjugate acid, or HX, for the iodide, and it has the weakest carbon to halogen bond, and so the reaction occurs the most quickly. So comparing the iodide 30,000 and the bromide 10,000, the chloride 200, and the fluoride's at 1. And these are the rates of reaction. So if you remember rates of reaction, this is referring to amount of reactant made to one reactant remaining. So 30,000 times we achieve the reactant compared to 1 time having the reverse reaction. Okay, bases and nucleophiles. Common bases and nucleophiles that are going to be used as the nucleophile in the nucleophilic reaction. So we have our electrophile, the CX molecule, carbon halide molecule is the electrophile. We also have to consider what is our base or our nucleophile. So common bases and nucleophiles that we're going to use to replace the halogen in a substitution reaction. So think about this base is going to be the Y that replaces the X in the SN2 reaction. So for example, remember we had the RX plus Y minus goes to RY and produces the halide ion. So we have a new RY bond, and so these are the Y groups. These are what are going to replace the X. And they're not necessarily listed in order of basicity. Okay, so you should be thinking about if you want to rank them in terms of how basic they are, you have to know what the pKa of the conjugate acid is. Let me get the laser pointer. Okay, laser pointer. So we have our common bases in nucleophiles include hydroxide ions, carbon oxide ions that we call, what we're going to do is depending on the number of carbons. So methoxide would be CH3O minus, ethoxide would be CH3CH2O minus, okay? We have water, alcohols, acetate ions, hydrogen sulfide, dioxide, dioxides like methyl dioxide, etc., and dihydrogen sulfide, diols, amide ion, a carbon amide, ammonia, primary amine, nitrile, acetylide ion, which this is the one we've already used in chapter 7 when we used the acetylide ion to make a bond to our RX. We were doing an SN2 reaction. So this is one that you already know. Remember, we had the acetylide and we said, okay, well, I want to add a methyl group to the carbon, so I'm going to react it with CH3Br, and the acetylide bonded to the carbon and the carbon bromide bond broke. This is an SN2 reaction. Okay, chloride, bromide, and iodide can be the nucleophiles. Under certain circumstances, they're on the weaker side of the nucleophiles shown here. Base strength and nucleophile strength. Stronger bases have a formal charge. Weaker bases are neutral. They're poorer nucleophiles. A negatively charged atom is a stronger base and a better nucleophile than the same atom as it is neutral. So hydroxide ion would be a better nucleophile than water. Methoxide ion would be a better nucleophile than methanol. Amide and ethyl amide. Okay, so ion, ethyl amide ion. So the negatively charged is going to be a better and stronger base and a better nucleophile than the neutral charge. That should be clear. They have more electrons because there are fewer atoms present, but the same number of total electrons. So the hydroxide ion has the same number of electrons as H2O. It simply has fewer atoms. And so the electrons are more concentrated. Base strength and nucleophile strength continued. So we covered the alkyl halide completely. We covered the carbon reactivity, substitution of the carbon affects reactivity. For the alkyl halide, we covered how the halogen affects the reactivity for the alkyl halide. And now we're looking at the base strength and how the nucleophile, the other reactant, the reactant other than the alkyl halide, affects the rate of reaction. The strength of the base is, of course, going to affect the rate of reaction. The strongest base, amide, will be the best nucleophile and will result in the fastest rate of reaction. So if you're trying to rank your bases, you could draw the conjugate acids and think about their pKa's, or you could just remember your trends in electronegativity, that the most electronegative is going to be the weakest base. So we have the pKa of 3 for HF, 16 for water, and 35 for ammonia. That means that the conjugate base of the one with the highest pKa is the strongest base. And this pKa for me is the easiest way that I keep track of strongest and weakest base. Polarizability. Polarizability is just a moment. Polarizability is the ability of an atom to move freely towards a positive charge. And polarizability increases as the atom gets larger. So we compare size going down a group. It's more significant of a change going down the group. We don't really compare size across a row. So that iodide being the largest atom of the halogens, it is the most polarizable because it is the largest, has the largest electron cloud, and those electrons are held less tightly by the positive nucleus because they're further away from the nucleus than they are in a smaller atom. And so those electrons in the outermost cloud of iodine are more freely able to move than the electrons in fluoride, which are very close to the nucleus. So the larger the atom, the more polarizable it is. So iodide is more polarizable. Polarizability versus nucleophilicity. So what does polarizability have to do with being a good nucleophile? It's going to actually depend on the solvent. The greater the polarizability of large atoms makes up for the decreased basicity. So iodide is a weaker base. It has a strong conjugate acid. But because it's polarizable, that helps it to be a better nucleophile. The greater polarizability of iodine helps make up for the decreased basicity. That makes them poor nucleophiles. So does polarizability affect whether it is a good nucleophile or not? It depends on the solvent. If the nucleophile, so if the nucleophile is in an aprotic solvent, then it is the poorest nucleophile. And the polarizability does not matter. But if the nucleophile is in an aprotic solvent, then it will be the best nucleophile because of the greater polarizability. It's really annoying me. Okay, so what is an aprotic polar solvent? This is the definition. An aprotic polar solvent has no proton bonded to a heteroatom. So we don't have an OH or an NH or an SH or etc. Okay? No proton bonded to a heteroatom. No OH, no SH, no NH. Example, tetrahydrofuran, THF. It's this cyclic 5-membered ring ether here. This is the solvent, remember, used for hydroboration oxidation. We'll use it as a solvent in other reactions as the semester continues. Okay. A protic solvent, then, is a solvent that has a proton bonded to a heteroatom. Examples, anything that contains OH, SH, or NH groups. For example, water, alcohol, thiols, amines, ammonia. These would all be considered protic because they have heteroatoms, oxygen, sulfur, or nitrogen, that are bonded to hydrogen atoms. All right, so for solvents, we have nonpolar solvents such as hexane and benzene. Then we have, and in nonpolar solvents, negatively charged species cannot dissolve. And so we would have to use a neutrally charged solvent or have very rapid mixing, and the solvent would never completely dissolve into the nucleophile would never completely dissolve into the solvent. Protic polar solvents have a hydrogen attached to an oxygen. That's your book's definition. But that is too limiting. Instead of oxygen, it should be heteroatom. So because also NH is a protic solvent, ammonia is a protic solvent in all of those groups. So heteroatom. And an aprotic solvent, they do not have hydrogen attached to a heteroatom, NH, OH, or SH. Okay, so base strength and nucleophile strength. And we're considering halides as nucleophiles in this comparison. The strongest base is going to be the best nucleophile unless they differ in size and they are in protic solvent. So if we are in protic polar solvent, then the best nucleophile will be the largest base, the one that is the most polarizable. And in that case, it would be iodine atom. When we consider these anions as nucleophiles. So we have size increases as we go to iodine, but basicity increases towards fluoride. Nucleophilicity in aprotic polar solvent is strongest for fluoride, but nucleophilicity in protic polar solvent is strongest for iodide. And this relates to polarizability and electronegativity. So if you look at why protic polar solvents make the strongest bases the poorest nucleophiles. So what we're talking about is in a protic polar solvent, fluoride is no longer the best nucleophile. It would be the best nucleophile in an aprotic solvent, but it's the worst nucleophile in a protic solvent. Why? And it is because of something that you learned in Gen Chem, solvation. The dissolution of ions as a result of ion dipole interactions. So for a polar protic solvent such as methanol, we have partial positive charges and in our dipole moment of the oxygen to the hydrogen. So the oxygen is partially negative and the hydrogen is partially positive. The partially positive hydrogen orients around the fluoride, which is negative. And there is a very strong ion dipole interaction between fluoride and the hydrogen because fluoride is a stronger and more electronegative ion. And in order for the ion to act as a nucleophile, the ion dipole interaction has to be broken. But iodide is a weaker ion. It's less electronegative and it's more polarizable. It still is solvated by the methanol, but the ion dipole interaction is weaker. And also the ability of the electrons to polarize or move more freely because it's a larger atom those electrons can break away from the ion dipole interaction more effectively. So fluoride is in a Protic solvent. You can say that fluorine is in a cage and it can't get out. But iodide is the escape artist, and the weak ion dipole interaction can be easily broken so that iodide can act as a nucleophile. Aprotic solvents. So what can we list some aprotic solvents for you? Yes, we have any solvent that doesn't have an OH bond or an NH bond is an aprotic solvent. Polar aprotic solvents, those are our favorites. Common polar aprotic solvents include NN-dimethylformamide and dimethyl sulfoxide. Being polar, they can solvate cations. And actually they solvate cations better than anions. And so they stabilize the cation or the partially positive carbon of the alkyl halide, but they don't interfere with the nucleophilic anion. And so the nucleophile is free to act as a nucleophile towards the alkyl halide. Steric hindrance can decrease nucleophilicity. So for our bases, we have to consider not only with the alkyl halide, considering steric hindrance for that, we also have to consider steric hindrance for the base. So ethoxide is listed as one of our possible nucleophiles, our RO- groups. RO- groups. So ethoxide ion is in this RO- group of nucleophiles, and so is tert-butoxide. Ethoxide is a better nucleophile, but tert-butoxide is a better base. And the reason that tert-butoxide is not a nucleophile but a base being a substance that's, your book describes a base as a substance that removes an acidic hydrogen. And a nucleophile being a substance that is not strictly isolated to acting as a base, removing an acidic proton. So ethoxide can substitute for a carbon group of an alkyl halide, whereas tert-butoxide cannot. And the reason that tert-butoxide is not able to substitute for a is not able to substitute for a halogen atom of an Rx alkyl halide is because it is sterically hindered. So let's look at an example. Its large size of tert-butoxide makes it difficult for it to approach the backside attack of a carbon. So here's a secondary alkyl halide, and I have drawn out the methyl groups to express how large they really are. And then you have to think about how large the methyl groups on the tert-butoxide would be if we drew out all the carbon to proton bonds instead of writing it as a methyl group. And then imagine the tert-butoxide attempting to make a bond to the oxygen. Okay? And the methyl groups of the two molecules are going to repel each other. We have atom-atom repulsion that is going, and we call that steric hindrance, and it's going to prevent the tert-butoxide forming a bond to carbon, and so it won't be able to act as that nucleophile that bonds to carbon and breaks the bond to the halogen X. So this, because of the methyl-methyl steric hindrance, which we can draw the I for, the clashing electron clouds will prevent this oxygen from forming a bond to the carbon and kicking off the halogen. Okay, so SN2 reactions can be used to make a variety of compounds. We're going to cover more what molecules can be made in chapter 10. This is a summary, and you should be able to show the mechanism for each of these reactions. The mechanism is going to be very consistently the same in the nucleophile forming a bond to the carbon, the bond to the halide or the group highlighted in yellow breaking. So the purple group attacks the carbon bonded to the yellow halide, and then the halide carbon bond breaks, and that is the mechanism. It's all in one step. You should be able to draw those two arrows that are required to show that mechanism. These reactions, the SN2 reactions, are irreversible reactions because a weak base cannot replace a strong base. And so another characteristic of an SN2 reaction is that the nucleophile that is replacing the halide should be a stronger base than the halide atom. So we talked a little bit about bromide and iodide as nucleophiles. An iodide would not be a nucleophile to an iodide, okay? If a halogen is going to act as a nucleophile, it must be a stronger base than the group that is leaving. And we're going to talk about nucleophiles replacing groups in chapter 10, which we'll cover in OChem 2. So in this case, hydroxide ion can replace the chloride because it is a stronger base than chloride. An oxide ion can replace an iodide because it's a stronger base. A sulfide ion can replace a bromide because it's a stronger base, and so on and so forth. Ammonia is definitely a stronger base than Cl-. And remember that we always go in the reaction is always going to go towards from stronger base to weaker base. So in this case, our halogens are the weaker bases. That means the reaction irreversibly goes in that direction. Next, we are looking at one specific example of making an amine. The first reaction of an ethyl halide with ammonia is going to produce a primary ammonium anion, but it actually won't stop at that step. So looking at an example, ethylamine reacting with methyl halide. So ethylamine being our nucleophile, donating a lone pair to the electrophilic carbon, and the carbon iodide bond then breaking. Now we have a methyl group bonded to our amine, but the amine having 4 bonds is positively charged, which is not favorable. When we treat with potassium carbonate, we're treating with a spectator potassium ion and our active and a base carbonate ion. So carbonate ion is actually going to deprotonate the nitrogen. So this carbonate ion deprotonates the nitrogen. So that we have the secondary amine, neutrally charged nitrogen that now has its lone pair back. That lone pair then is free to react with a second molecule of methyl iodide, and then it returns to being a protonated amine. But now it's a tertiary protonated amine. It will actually react again with the carbonate ion, removing the last proton bonded to nitrogen and the bonding electrons going back to nitrogen. Those bonding electrons then can react once more with the methyl iodide to form the quaternary ammonium iodide salt. So we can make a quaternary amine, which is one of the group 1 compounds that we discussed on the second slide. So substitution reactions. Continuing on to, we're going to cover now a second type of substitution reaction. This is a good place to stop, and we'll start with the second type of substitution reaction, not SN2, on the next video.